Okay, so what we're going to be doing now is we're going to use the equilibrium constant to calculate equilibrium concentrations. So in this question, we're given even less information. So look at the reaction below where we have carbon monoxide reacting with water to produce carbon dioxide and hydrogen gas. Now, the question reads, the reaction has an equilibrium constant of 4.06 at 500 degrees Celsius. If 0.2 moles of carbon monoxide and 0.2 moles of water are placed in a 2-liter reaction vessel, what are the concentrations of the reactants and the products when the system reaches equilibrium? So in this one, we're not given the concentrations, we have to find them. All we're given is the equilibrium constant. So let's go ahead and start working this problem out. What we have to do first is we have to calculate the molarity. Remember that molarity is equal to the moles divided by the liters. So in this situation, we have 0.200 moles of CO, and we're going to divide that by the 2.00 liters of the vessel. If you get that, you're going to end up with 0.100 molar concentration of CO. Because the H2O is at the same concentration, right, then we can assume that we have 0.100 molar concentration of H2O. Okay, so that makes things a little bit easier. Now, when we're working this out, just like we did in the last problem, right, we're going to use our ice chart. Okay, so remember that the ice chart is the initial concentration, the change in concentration, and the equilibrium concentration. That's what it stands for, ice. Okay? Now, let's take a look at our table here, and let's do our reaction. Now, our reaction is going to be the concentration of CO, gas, plus H2O. That's going to go to equilibrium to form CO2 gas, okay, and H2, or hydrogen gas. So as you can see, this is all a homogeneous equilibrium. They're all in the same state, right? Okay, so we have our initial concentrations. It's 0.100 of each one of these, right? So what we're going to do now is we're going to go in and we're going to fill in our values. So let's fill in our values. So the initial concentration for this reaction using our ice chart is going to be 0.100 for carbon monoxide, 0.100 for water. And remember, at the beginning of the reaction, there should be no products, so those are going to both be at 0.00 molar concentration, right? So that's it, right? So far, that's what we have. Now, the change in the concentration is where it's going to get a little bit tricky because we really don't know by how much it's changing. So all we're going to do is we're going to have to use variables, okay? Now, keep in mind that the reactants change is going to be negative because they're forming products, and the products change is going to be positive. Okay, so in this case, because we don't know the change, we're going to just use as a minus x, and a plus x for the products because they're forming, and a plus x for the other product because it's also forming. Now, keep in mind that all this is a 1-to-1 ratio. That's why you only have a 1x for all across the board here. Okay, so when we get to the concentration at equilibrium, it's basically taking these values and combining them, right? So let's go ahead and do that. So at equilibrium, the CO, or the carbon monoxide, is going to be at 0.100 minus x, 0.100 minus x, and of course 0 plus x is just going to give you x and x. Okay, so we filled out our chart. So now that we have our chart, right, then what comes next? Well, this is now where we set up our mass action equation, right? Okay, so let's go ahead and get that going. We know that the equilibrium constant, right, is going to be equal to the concentration, the molar concentration of the products over the molar concentration of the reactants. Okay. Now, in the question, if you recall, we were given the value of Kc. So this mass action equation can actually be set equal to 4.06, right? So here we have our equation set up. So now that we know how our mass action equation is going to be set up, now we can go through and plug everything in. Therefore, here's what we got. The concentration of the CO for what we know right now is worth X. The H2 is X. The carbon monoxide is 0.100 minus X. And the water is 0.100 minus X. That is also equal to 0.406. Okay? Here's where we're going to have to do some algebra. Let's go ahead and simplify this out just a little bit. Okay? If I multiply X times X, I'm going to end up with X squared. And if I multiply these two here, I'm going to end up with the same thing, which is 0.100 minus X, and I'm going to square that. That's still going to be equal to 4.06. All right? Now, I want to simplify this a little bit, right? I want to get rid of these squared. So how do you undo a square? You take the square root. So I'm going to take the square root of X squared over the square root of 0.100 minus X squared is equal to the square root of 4.06. So what happens here is the square root cancels, right? Square root cancels, and here's what I have. X over 0.100 minus X is equal to the square root of 4.06, which is 2.01. Okay? Now, again, all this right now is algebra, right? So what I'm going to do now is I'm going to take this unit, or this piece here, the denominator, and I'm going to bring it over to the other side. How do I do that? I'm going to multiply by on both sides. So 0.100 minus X. Let me see here. 0.100 minus X. What that does is it cancels here. Okay. And then I'm left with X is equal to 2.01 times 0.100 minus X. Okay. Again, just basic algebra at this point. Let's go ahead and distribute this here. And so we can simplify. X is then going to be equal to 0.201 minus 0.201 X. Okay. All right. A little correction here. Put the decimal in the wrong place. Okay. So here we are. This is where we're at right now. So I'm going to go ahead and swap here. So right now we're sitting at X is equal to 0.201 minus 2.01 X. Okay. Again, all algebra at this point. So now we can combine like terms, right? So let's take a look. If I add 2.01x to both sides, I'm going to end up with x plus 2.01x is equal to 0.201, right? If I add those, I'm going to end up at 3.01 x is equal to 0.201. And if I want to solve for x, I'm going to divide both sides by 3.01. All right. And if I take that, x then is equal to 0.0668. Okay, so let's recap. I'm going to go up a little bit. We set up our ice concentrations, right? And we ended up here at equilibrium. We set up our mass action equation, right? And we figured out that it's equal to K, to the equilibrium constant. We substituted the variables that we put in our ice chart into our mass action equation. And then from here, all we did was solve for x. So if you have trouble with the algebra, review a little bit, okay? We solved for x, and we've determined that x then is equal to 0.0668, okay? Now, what does that mean? Well, if you look at our ice chart, now everywhere we see an x, then we substitute that value. And then we can determine the concentrations of the product and the reactants, right, at equilibrium. So let's do one at a time. If I look at CO, which is carbon monoxide, the first reactant, right? Then at equilibrium, the value was 0.100 minus, now I'm going to put in this value, which is 0.0668, right? And that's going to give me a value of 0.033 molar concentration at equilibrium for carbon monoxide. Remember that water had essentially the same concentration at equilibrium minus, this is going to be 0.0668 is equal to 0.033 molar concentration at equilibrium for water. CO2, remember that CO2 was equal to X, so then X is equal to 0.0668 molar concentration. And of course, hydrogen gas was the same as the CO2 at equilibrium. So hydrogen gas also has a molar concentration of 0.0668 molar. Okay, these are both at equilibrium. Okay, so these are your answers. This is a little bit more algebra, but using the same methods of setting up our mass action equation here, replacing our ice values here, and then just doing the algebra to solve for x, you should be able to determine the molar concentrations of the products and the reactants at equilibrium.